Right. So when an electron jumps down from the n1th orbit to the n2th orbit, where n2 is less than n1, it releases energy. Higher the orbit or greater the orbit number, greater the energy of the electron, lesser the orbit number, lesser the energy of the electron. So when it jumps from a higher orbit to a lower orbit, it releases energy. And how much energy does it release? Energy in the first orbit where it was, minus energy in the final orbit where it lands. Okay, so just subtract them. You'll get it as 13.6 z square, 1 by n2 square minus n1 square in 1 by n2 square minus 1 by n1 square in electron volts. And that energy will be released in the form of a photon. And the formula for energy of a photon given by Einstein is hc by lambda. So equating these, adjusting, we get 1 by lambda is equal to rz square, 1 by n2 square minus 1 by n1 square. So this formula helps you derive the wavelength of radiation emitted when an electron jumps from orbit number n1 to orbit number n2. Okay, so to basically to emit radiation, the final orbit number should be less than the initial orbit number. You can use the same formula with a minus sign to find out the wavelength absorbed by an electron. Okay, basically when it goes from a lower orbit to a higher orbit, it absorbs energy. Okay, it has to absorb energy. So you can find out what is the wavelength absorbed. And R value last class, I had mistakenly given this as 1.01 into 10 power 7. It's actually close to 1.1 into 10 power 7 per meter. Okay, 1.09, you can take it as 1.1. In some problems, they'll ask you to take it as 1 itself. Okay. So we'll be working on this formula today. 1 by lambda is equal to rz square, 1 by n2 square minus 1 by n1 square. Okay. Remember, all this is valid only for a single electron species. Basically, in Bohr's model, you can apply this. Bohr's model is valid only for single electron species. One electron should be revolving around the nucleus. Okay. Now, the energy of electron in the nth orbit is given by minus 13.6 z square divided by n square. Okay. Consider the hydrogen atom. For hydrogen, the atomic number is 1. Therefore, energy of nth orbit can be simply written as minus 13.6 divided by n square in electron volts. Okay, the unit is also important. Fine. So in the first orbit, n is equal to 1, which is called the ground state of the electron, the energy is going to be minus 13.6 electron volts. Let's say this is the ground state. N is equal to 1. The energy is minus 13.6 electron volts. Next, if you substitute n as 2, the energy becomes minus 13.6 divided by 2 square. That is minus 13.6 divided by 4. That will be about 3.4, minus 3.4. So in the second orbit, right, for which the principal quantum number n is equal to 2, the energy of electron, okay, in the second orbit of hydrogen atom will be minus 3.4 electron volts. Okay. Now, what is the energy gap between these two orbits? Minus 3.4 minus 13.6. The difference in energy is 10.2 electron volts. What does this mean? An electron which is in the first orbit, if it somehow attains an energy of 10.2 electron volts, it can make a transition. It can jump up to the second orbit. That is what it means. And you can think of it in reverse also. An electron which is in the second orbit is called first excited state. An electron which is in the first excited state, if it loses an energy of 10.2 electron volts, it will come down to the ground state. N is equal to 1 is called ground state. Okay. Now suppose N is equal to 3. Just a moment. If n is equal to 3, you get the energy as minus 13.6 divided by 9. That becomes 1.51 electron volts, minus 1.51 electron volts. So the third orbit, energy of electron in the third orbit will be minus 1.51 electron volts. And what's the energy difference between the second orbit and the third orbit? 1.51 and 3.4. If you subtract, how much does it become? 1.89. Okay. Electron volts. Okay. So an electron which is in the second orbit, if it attains an energy of 1.89 electron volts, it can jump to the third orbit. Okay, exact that much amount of energy it will need. Likewise, you can find out energies of the other orbits as well. Energies of electron in the other orbits as well. In the fourth orbit, n is equal to 4. The energy of electron becomes minus 13.6 divided by 4 square, 16. That is 0.85 electron volts. And there will be a certain energy difference between the fourth orbit and the third orbit, and so on. Okay, let's just draw one more energy level. For n equal to 5, the energy of the electron will be minus 13.6 divided by 25, that is minus 0.54 electron volts. Fine. So by calculating the energy of two particular orbits, you can tell how much energy the electron will require to jump from a lower orbit to a higher orbit. You can also tell how much energy it will release when it jumps from a higher orbit to a lower orbit. Okay. Let's quickly solve one problem based on this. Suppose an electron jumps from third excited state to ground state. First, calculate the energy released. And you know this energy will be released in the form of radiation, okay, in the form of a photon. Calculate the wavelength of radiation released. Solve this quickly. Third excited state to ground state. Find out the energy released and the wavelength of radiation that is emitted. Okay, this is very easy actually. It jumps down from the third excited state to the ground state. Now, which orbit is the third excited state? N is equal to 4. So it is jumping from n is equal to 4 to n is equal to 1. So the initial energy of the electron is minus 0.85 electron volts. And the final energy of electron is minus 13.6 electron volts. Simple. So if you want to find out the energy released is initial energy minus final energy. So minus 0.85 minus of minus 13.6 in electron volts, and that would be, just a moment, 13.6 minus 0.85, 12.75 electron volts. That's the energy released, and this will be released in the form of radiation, electromagnetic radiation. Okay, now how do you find out the wavelength of radiation? This energy that is released will become the energy of a photon, and we have a formula for energy of a photon, hc by lambda. So you can write 12.75 electron volts is equal to hc by lambda. And for calculations like this, okay, you better remember the value of hc. It is 1240 electron volt nanometer. Now energy 12.75 is in electron volts itself. Okay, I'll write the unit also. Equal to 1240 electron volt nanometer. The unit electron volt will get cancelled. And you'll get wavelength in nanometers. You can say that lambda is equal to 1240 divided by 12.75 in nanometers. and 1240 divided by 12.75 is about 97.25 nanometer. That's the wavelength of radiation emitted when an electron makes this jump. Okay. Now, we had discussed a formula in the last class also to find out the wavelength of radiation emitted. This one, 1 by lambda is equal to rz square, 1 by n2 square minus 1 by n1 square. Let's try using this and see if we get the same answer or not. Directly, if you know from which orbit to which orbit it is jumping, you don't always have to calculate energy to find out wavelength. You can use this formula. So 1 by lambda is equal to r. R is 1.1, approximately 1.1 into 10 power 7. That is in meter inverse. Okay, unit is also important. Z square, we are talking about hydrogen, so Z square is 1 into 1 by n2 square minus 1 by n1 square. Now from which orbit to which orbit did it jump? Fourth orbit to the first orbit. So n1 is 4 and n2 is 1. So basically it becomes 1 by 1 minus 1 by 4 square, 16. Okay. Therefore, this is 1 by lambda. 1 minus 1 by 16 is 15 by 16. So this bracket can be written as 15 by 16. Then this is 1 by lambda. Therefore, lambda becomes 16 by 15 into 1.1 into 10 power 7, and that answer is in meters. Okay. If you want the answer in nanometers, multiply with 10 power 9 and you get the answer in nanometers. And 16 divided by 15 further divided by 1.1 is 0.97. So we get 0.97 into 10 power 9, sorry, into 10 power 2 nanometers. That is around 97 nanometers. And you see that the answer is almost the same. Okay. So if you want to just find out the wavelength emitted when an electron makes a certain transition, you can use this formula directly. You don't have to always calculate energy. Okay. So here we have derived the energies of certain orbits, okay, in a hydrogen atom. Fine. Now, when an atom is in an excited state, or when an electron is in an excited state, it will eventually lose energy and come down to the ground state. Fine. Suppose there's an electron in any one of the higher orbits. Higher orbits means n equal to 2 onwards. They are all called higher orbits for n is equal to 1. So suppose there's an electron in n equal to 2 state. It could lose energy and jump down to n equal to 1. Suppose there's an electron in n equal to 3, second excited state. It could also lose energy and jump all the way directly down to the first orbit. Okay. An electron in n equal to 4 also could lose energy and jump all the way to the first orbit. Okay. Come down to the first orbit and so on. So an electron in any of the higher orbits can lose energy and end up in the ground state directly. There's no necessity that the electron should come down step by step. There's no rule that the electron should come down step by step. What the electron does, we cannot really tell. Okay, you will be doing some probability based calculations in your engineering. Okay, it involves quantum physics. For now, you don't have to bother about which jump the electron is going to make. For example, the electron in n equal to 5, it can jump to n equal to 4, it can jump to n equal to 3, it can jump to 2, it can jump to 1 also. Which jump it is exactly going to make, those calculations are not required for now. Okay, but it's possible that it comes down to n equal to 1 directly. Okay. Now, when an electron in any one of the higher orbits of hydrogen jumps all the way to the first orbit directly, you will get a series of wavelengths. Okay. The jump 2 to 1 will emit one wavelength. The jump 3 to 1 will emit one wavelength. The jump 4 to 1 will emit one wavelength, and so on. Okay. The last orbit is n is equal to infinity, or n tends to infinity. Okay. Infinite number of orbits will be there in an atom. And what will be the energy of electron in that orbit? 0. Okay, so that jump is also possible from the infinite orbit all the way to the first orbit. Okay. Now, for all these jumps, or for each of these jumps, there will be a wavelength associated. Okay. Now, this set of wavelengths, which can be emitted when an electron jumps from any higher orbit directly to the ground state, is called, this set of wavelengths is called the Lyman series of wavelengths. Okay, and we are talking about hydrogen atom. Fine. The wavelength emitted, okay, or the radiation emitted when an electron jumps from n equal to 2 to n equal to 1. Okay, see, this jump from 2 to 1 is the first jump that can happen, or is the most basic jump that can happen in the Lyman series. So this is called the, this jump is called the first line of the Lyman series. Okay, you have to remember this naming. First line of Lyman series is from n equal to 2 to n equal to 1. And this jump from the last orbit to the first orbit is called the last line of the Lyman series. Okay, and other numbers you can understand. First line is from 2 to 1. Second line will be from 3 to 1. Third line will be from 4 to 1, and so on. Last line will be from orbit number infinity to orbit number 1. Okay, so this set of wavelengths emitted is what we call as Lyman series. Okay, now we are talking about hydrogen atom. We are talking about the emission spectrum of hydrogen atom. What are the different wavelengths that a hydrogen atom can emit when it goes from higher energy states to lower energy states? Okay, this set of wavelengths is called the emission spectrum, and Lyman series is part of the emission spectrum of hydrogen. Okay, it is part of the many different wavelengths that it can emit. Okay, let us derive the wavelengths of first line and last line of the Lyman series. Do this quickly, all of you. I think you can do it on your own. You know the orbit numbers, right? And if you know orbit numbers and the atomic number Z is 1, you should be able to tell lambda values. Okay, I'll derive the first line, you derive the last line. So in the Lyman series of hydrogen atom, if you want the wavelength of the first line, you calculate it as 1 by lambda 1 is equal to, what is the formula? Rz square into 1 by n2 square minus 1 by n1 square. R is 1.1 into 10 to the power 7 per meter. Okay, by using this, you will get wavelength in meters, and then you can convert it to nanometers. Z square for hydrogen is 1 multiplied with 1 by n2 square. The final orbit number in Lyman series is 1. Initial orbit number depends on which line you want. First line means initial orbit number is 2. So 1 by 2 square. So 1 minus 1 by 4, 3 by 4. So if you invert this, you get lambda 1. Wavelength of the first line of the Lyman series is 4 divided by 3 into 1.1. So 4 by 3 by 1.1. It's about 1.21. Okay. Into 10 power minus 7 meters. And meter is 10 power 9 nanometers. So this is about approximately 121 nanometers. And a wavelength of 121 nanometers, it's clearly less than 400 nanometers. Why are we bothered about 400? Wavelengths less than 400 nanometers fall in the ultraviolet region. Okay, so this is UV radiation. So the first line of the Lyman series, okay, is a UV radiation, falls in the UV range. Hope this is clear to all of you how to find out the wavelength emitted for any line of a spectral series. So for the first line, this is the wavelength. The jump is from n equal to 2 to n equal to 1. Okay. The last line, the jump will be from infinity to 1. So do this, all of you. Find out the wavelength emitted, or find out the wavelength corresponding to the last line of Lyman series of hydrogen. The formula is the same. R Z square 1 by n2 square. The final orbit is the first orbit itself, minus 1 by n1 square. First orbit or the initial orbit is infinity. So, okay, this is quite easy actually. I don't have to wait for you to solve. Invert is 1 by 1 minus 1 by infinity is 0 anyway. So this bracket, this whole bracket becomes 1. Therefore, wavelength of the last line of the Lyman series is 10 power minus 7 divided by 1.1. Okay. And that's in meters. If you want in nanometers, multiply it with 10 power 9. So 100 divided by 1.1, that is close to 90.9. Okay. We'll take it as 91 nanometers. Let it be. This is also in the UV region itself. Fine. So every line of the Lyman series falls in the UV range. Okay. So the entire Lyman series of hydrogen is ultraviolet radiation. So hydrogen atom is capable of emitting UV radiations. Okay. If the electron of the hydrogen atom jumps from any of the higher states directly to the ground state, it emits UV radiation. Okay. Now it's also possible that an electron jumps from one of the higher orbits to n equal to 2. Just a moment. Okay. Suppose an electron is in the orbits n is equal to 3 or 4 or 5 or any of the higher orbits. Consider an electron in the orbit n is equal to 3. It's possible that it jumps to n equal to 2. Consider an electron in the orbit n is equal to 4. It's possible that it jumps directly to n equal to 2. Okay. From 5 also it could jump directly to n equal to 2. And so on. Okay. From infinity also it can jump to n equal to 2. Now, for each of these jumps, okay, from a higher orbit to orbit number 2, for each of these jumps, there will be a wavelength associated. Okay. This set of wavelengths is what you call as the Balmer series. So Balmer series is also a part of the Balmer series is also part of the emission spectrum of the hydrogen atom. It is also a set of wavelengths that a hydrogen atom can emit. Fine. Then the first line of Balmer series will be from n equal to 3 to n equal to 2. And the last line of Balmer series will be from n equal to infinity to n equal to 2. Okay. So for Balmer series, the final orbit number n2 is always 2. Initial orbit number depends on where the electron is jumping down from. Okay. So do this calculation, both of you. Lambda, wavelength of the first line of Balmer series. And then wavelength of the last line of the Balmer series. Solve quickly. I'll give you all 3 minutes. Any answer? Okay. See, first line of Balmer series would be from n equal to 3 to n equal to 2. Okay. Directly substitute in that formula. I asked you to consider R as 1 into 10 power 7 instead of 1.1. So 1 by lambda is R, z square is 1 into 1 by n2 square minus 1 by n1 square. Simple. 1 by 4 minus 1 by 9 becomes 5 by 36. Invert it, you get wavelength as 36 by 5 into 10 power minus 7 meters. You can write it as into 10 power 2 nanometers directly. Okay. 36 by 5 is how much? 7.2. So that is approximately 720 nanometers. That's the wavelength of the first line of the Balmer series. Okay. Then the last line. The final orbit number in Balmer series is 2. For the last line, the initial orbit number will be infinity. 1 by infinity is 0. So this becomes 10 power 7 divided by 4. Simple lambda of the last line of Balmer series will be 400 nanometers. Okay, if you take R as 1 into 10 power 7. Now see, 400 nanometers, 720 nanometers, all this is in the visible range. Okay, so remember the entire Balmer series of hydrogen atom, okay, falls in the visible range of the electromagnetic spectrum. Lyman series is in UV range, Balmer series is in visible range. And there's absolutely no overlap. The first line wavelength of Lyman series was 121 nanometers. Okay. Last line wavelength of Lyman series was 91 nanometers. Fine. For the Balmer series, it is 720 to 400. Okay. There's absolutely no overlap between Lyman series and Balmer series. Okay. And always remember, higher the number of the line. Okay. For example, when you go from first line to last line, whether it's the Lyman series or Balmer series or any other series, first line involves the nearest orbits, last line involves the farthest orbits. Okay, nearest orbits means least amount of energy difference. Least amount of energy difference corresponds to highest wavelength emitted. So first line of any series will correspond to a greater wavelength. Last line will have more energy difference, means less wavelength of radiation emitted. Last line wavelength will be less. Okay, you have to remember these patterns also. So in Lyman series, first line wavelength was 121, last line was 91. Okay. Balmer series, first line is 720, last line is 400. Okay, so last line wavelength will be less than first line wavelength always. Fine. Next, it's also possible that an electron jumps from one of the higher orbits to n is equal to 3. Okay. Like it can jump from n is equal to 4 to n equal to 3. Five to 3, 6 to 3, and so on up to infinity to 3. Okay. And for each of these jumps, there will be a certain wavelength associated, wavelength of radiation associated. This series of wavelengths, okay, what is it called? Lyman, Balmer, what is the third one? Paschen series. And for the Paschen series, the final orbit in which the electron ends up is 3. Initial orbit could be any number greater than 3. Okay, it depends on which line they want to ask you about. So the first line corresponds to 4 to 3 and the last line corresponds to infinity to 3. Okay, let's quickly find out the wavelengths of first line and last line of Paschen series. Wavelength of the first line, R, let's take it as 10 power 7 itself. Z square is 1 because we are dealing with hydrogen, divided into 1 by n2 square minus 1 by n1 square. Okay, 1 by 9 minus 1 by 16. 9 and 16, you can take it as 144. So 7 divided by 144. Therefore, the wavelength becomes 144 divided by 7 into 10 square nanometers. 144 divided by 7. Okay. Turns out to be around 2000 something. Fine. Into 100 if you do. Close to 2000 nanometers. Let it be. Okay. Then lambda of the last line of the Paschen series. 10 power 7 into 1 by 3 square minus 1 by infinity. 0. Effectively, this becomes, okay, this is 1 by lambda, sorry. Okay. So if you invert this, you get lambda of the last line as 9 divided by 10 power 7 in meters. And in nanometers, it will become approximately 900 nanometers. Now, 2000 nanometers, 900 nanometers, all these are above 700 nanometers or comfortably above 720. So the Paschen series of hydrogen emission spectrum of hydrogen falls in the infrared region. of the electromagnetic spectrum, not just the Paschen series, any of the higher spectral series. Okay, like if an electron jumps from any of the higher orbits to n equal to 3, you call it the Paschen series. Any higher orbit to n equal to 4, okay, like 5th orbit to the 4th orbit, 6th to 4th orbit, or infinity to the 4th orbit. Lyman, Balmer, Paschen. I think the next one is called Pfund series. No, Brackett and then Pfund. Okay. This, when the electron ends up in n equal to 4, call that as the Brackett series. Final orbit number is 4. Okay, you can tell what is the wavelength of first line, last line by substituting in that calculation, in that formula. And if an electron ends up in the 5th orbit, okay, like 6 to 5, 7 to 5, or all the way from infinity down to 5. This series of wavelengths is called the Pfund series. The final orbit number is 5. In that also, you can tell what is the first line and the last line. So you need to remember these names. In the Lyman series, remember electron ends up in the first orbit, ground state. Balmer series, second orbit. Okay, Paschen series, third orbit. Brackett, fourth orbit. Pfund, fifth orbit. Okay. And questions based on this are very, very common. They can ask you wavelength of any line of any of these spectral series. Okay, so you need to remember the number, the name of the series, and for each series, which is the number of the final orbit. Okay, that you need to remember. And how to write the line number you need to know. For example, first line of Brackett series will be from 5 to 4. Brackett series, the final orbit is the 4th orbit. Then the first line will be from 5th to 4th. That way you have to calculate the line number. And based on the line number, you have to calculate the jump. Okay? Then you can find out the wavelength by substituting in that formula. Okay. And an electron can even do the reverse. It can jump from a lower orbit to any of the higher orbits, right? By absorbing appropriate amount of energy or by absorbing radiation of an appropriate amount of wavelength. Okay, for example, suppose there's an electron in the ground state. Fine. If it absorbs exactly 121 nanometer radiation, electron in ground state absorbs 121 nanometer radiation, then what it will do? How did we get this 121 nanometer? We took the jump from n equal to 2 to n equal to 1, then it emits 121 nanometer. If it absorbs 121 nanometer, it can do the reverse of that jump. It can go from n equal to 1 to n equal to 2. Okay. So the set of wavelengths that it can absorb are called absorption spectrum. Okay. That whole set or list of wavelengths is called the absorption spectrum of the atom. When it jumps down, it emits. That list of wavelengths it emits is called the emission spectrum. Okay. And there's one more calculation you should be able to do based on all this. When an electron is in a particular orbit, okay, let's say electron is in the second orbit. How many different wavelengths can it emit? Means how many different jumps can it do? From second state, the only jump it can do, okay, and emit energy is jumping to the ground state. So from second state, if an electron is in second state, there is only one possible wavelength that it can emit. Okay. Suppose the electron is in the third state. Okay, third orbit, I should not call it third state, third orbit. Then from n equal to 3, it can jump to n equal to 2 and then n equal to 1. There it emits two wavelengths. Okay, or it can jump directly to n equal to 1. So the total number of different wavelengths it can emit as the atom gets de-excited is 3 for the third orbit. It's only 1 for the second orbit. Okay, so how many different wavelengths it can emit while the atom gets de-excited, you should be able to calculate. Okay, but let's see, let's try to find a sequence in this. For for the second orbit, it's only 1. From the third orbit, it is 3. Suppose electron jumps from the fourth orbit. Okay, what all are possible? It could go from 4 to 3. It could go from 4 to 2. It could go directly from 4 to 1. And then what it can do is, if it goes 4 to 3, then it can do 3 to 2, 2 to 1. And if it goes from 4 to 2, okay, 2 to 1 is taken care of anyway. It can jump directly from 3 to 1 also. Okay. Right. So observe, there is a pattern that you can see here. From the second orbit directly to the ground state, there's only one jump possible. Okay. So if it is jumping from n equal to 4, how many different wavelengths are possible? 1, 2, 3, 4, 5, 6 wavelengths are possible. Jumping from n equal to 4. Okay. So there is a sequence here that you can observe. Now see, from 2 to 1, there's only one line possible. Put it aside. If it jumps from 3, okay, if the initial orbit number of the electron is 3, you can see that 3 to 2 is one extra line. 3 to 1 is an extra line compared to the first jump that is possible. Okay. So from n equal to 2, when it jumps, number of possible wavelengths that it can emit is just 1. Okay. But when it jumps from n is equal to 3, when it is initially in orbit number 3, this 1 is possible, and in addition to this 1, 2 more are possible. 3 to 2 and 3 to 1. Those possibilities are there. Next, if it is initially in the orbit number n is equal to 4. Now see, while jumping from the third orbit, 3 different wavelengths are possible. That set of 3 different wavelengths is included while jumping from the fourth orbit also. In addition, you get another 3 wavelengths. Okay, 4 to 3, 4 to 2, 4 to 1. Okay, so the total number of possible wavelengths that can be emitted when it jumps from the fourth orbit, or when it begins jumping from the fourth orbit, is 1 plus 2 plus another 3. Okay, whatever jumps are possible while jumping from the third orbit, plus another 3 new jumps are possible while jumping from the fourth orbit. Okay, similarly, if it is jumping from the fifth orbit, okay, what it can do is it can go 5 to 4, 5 to 3, 5 to 2, 5 to 1, and in addition to this, it can do all the jumps which can be done from 4 to 1. Okay, so if it goes from 5 to 4, after that it could go 4 to 3, 4 to 2, 4 to 1. If it goes from 5 to 3, after that it could do 3 to 2, 3 to 1. And it could, if it goes from 5 to 1, 5 to 2, after that it could do 5 to 1. Okay, so the entire set of 6 wavelengths which are possible while jumping from n equal to 4, that set of 6 wavelengths you will get here. In addition, you will get another 4. So totally 10 different wavelengths are possible while jumping down from n equal to 5. So if it is jumping from n is equal to 5, the total number of possible wavelengths is 1 plus 2 plus 3 plus 4. So now I think you can see the pattern. Depending on the orbit number from which it is jumping, you can calculate how many different jumps, how many different jumps or how many different wavelengths are possible. So basically, if it is jumping from, let's say n is equal to n naught, which numbers will you have to add? 1 plus 2 plus 3 plus so on up to n naught minus 1. So basically, this is summation of all natural numbers. Okay. Summation of all natural numbers from 1 to n naught minus 1. And we have a formula for summation of the first n natural numbers. N into n plus 1 by 2. Okay. Here you have to add the first n minus 1 natural numbers. So it becomes n into n plus 1 by 2. Basically n naught into n naught minus 1 divided by 2. Okay, where n naught is the orbit number from which it is jumping. For example, if it is jumping from the second orbit, you take n naught as 2. Then 2 into 2 minus 1 is 1 divided by 2, you get one jump, one possible jump. Suppose it is jumping from the third orbit. Then it becomes 3 into 3 minus 1 divided by 2. 3 minus 1 and 2 cancel. 3 jumps are possible. Correct. If it's jumping from the fourth orbit, 4 into 4 minus 1 by 2. 2, 4, it's 2 times. 2 into 3 is 6 jumps are possible. If it is jumping from the fifth orbit, 5 into 5 minus 1 by 2. 5 minus 1 is 4. 4 into 2. So this becomes 10 possible wavelengths. Okay. So n naught into n naught minus 1 divided by 2. This gives you the number of different possible wavelengths an electron can emit while jumping from a particular orbit downwards. Okay. Spectral series, wavelengths, number of possible jumps. Fine. Now, Bohr proposed this idea of stationary orbits. He said that in a stationary orbit, the angular momentum MVR of an electron is nh by 2 pi. He said it's an integral multiple of h by 2 pi. He didn't explain why it was like that. Okay, I got one question. What if the final orbit is not 1? Then do we have to subtract? Pradyumn, can you unmute and ask clearly? Like, I didn't understand your question. Okay, is it about this formula? See, this formula doesn't require the final orbit number to be 1. This formula just tells you how many different jumps are possible. Okay, while going down from a certain state, certain higher state. If you want to eliminate some possibilities, then you will have to subtract, that's all. Suppose you want to know how many different jumps are possible when an electron goes from n is equal to 5 to n is equal to 3. Okay, then you will have to look for the difference between the orbit numbers. Okay, suppose you want number of, okay, in chat you are asking n is equal to 8 to n is equal to 3. Okay, let's say you want to do that. You want to find out how many different transitions are possible when it goes from n equal to 8 to n equal to 3. Now 8 to 3, the gap is 5 orbits, right? 3 plus 5 is 8, correct. So in between there will be 4, 5, 6, 7, and this is the 8th orbit. Now 8 to 3, the number of different possibilities will be same as 7 to 2. And it will also be same as 6 to 1. And you have a formula for this. Okay, it just depends on number of levels. No, number of different jumps depends on number of levels. Okay, so 8 to 3, the number of different jumps possible will be same as the number of jumps possible from 7 to 2. And it will be same as number of jumps possible from 6 to 1. Okay, and you know how to calculate 6 to 1. Okay, good question anyway. Such questions also can be asked. Okay. Now, Bohr proposed the idea of stationary orbits, and what is special about stationary orbits is that the angular momentum of an electron is quantized. MVR is equal to nh by 2 pi. De Broglie supported this theory given by Bohr. See, what is the basic study that De Broglie did? He proposed wave nature of particles, and he gave a formula for the wavelength of matter. Lambda is equal to h by mv, right? So how did De Broglie support Bohr's hypothesis? Okay. What De Broglie said is, an electron revolves in an orbit without emitting radiation. Okay, that means an electron revolves in a stationary orbit only if the wavelength of the electron, only if the circumference of the orbit is an integral multiple of wavelength of the electron. Okay, so De Broglie gave another statement, or you can say De Broglie proposed something which adds to the specialty of the stationary orbits. Okay, he said that in a stationary orbit, the circumference of the orbit, so 2 pi r, okay, should be an integral multiple of wavelength of the electron. Now, electron has wave nature. It has been proved experimentally also in the, what is it? Davison-Germer experiment. Okay, so electron has wave nature. So what de Broglie said is that the circumference of the orbit should be an integral multiple of wavelength of an electron. Only then the electron can stay in that orbit without giving out energy. And that automatically becomes a stationary orbit. So if an electron is in a stationary orbit, then if you treat electron as a wave, situation should be like this. Okay. The circumference of the orbit should be an integral multiple of the wavelength of the electron. Only then electron can revolve without radiating energy. Okay. Now 2 pi r should be equal to n times of the wavelength. And treating electron as a particle, treating electron as a wave, its wavelength becomes h by mv, right? Therefore, you send mv this side, 2 pi that side, you get mvr is equal to nh by 2 pi. And this is what exactly Bohr said. Okay, so de Broglie hypothesis kind of supports Bohr's theory of the atom. Okay, so it, what can you say? It gives more, okay, fine. It supports Bohr theory. It, what should I say? Anyway, it kind of proves the existence of stationary orbits. Okay. Fine. That is all there is in this chapter. Basic model of the atom, how to do calculations based on energy of the nth orbit, radius of the nth orbit. They can even ask you time period of revolution of electron in the nth orbit. Even speed of revolution can be asked. You don't need to know the exact values, but you should be able to do ratio based calculations. Now, when an electron is in an orbit, it revolves in the orbit under the influence of electrostatic force from the nucleus that behaves as a centripetal force. Centripetal force can never change the speed of an object. It can change direction and make it go around in a circle, but it cannot change the speed. Therefore, electron in a stationary orbit executes uniform circular motion. And for uniform circular motion, you can define a time period of revolution. You can even find out the speed of revolution, speed, angular velocity. Okay, just a second. Okay. Suppose you want to find out the speed of revolution of an electron in a certain orbit. Okay, the basic formula. We equate the centripetal force to mv square by r, and then we use Bohr's idea that mvr is equal to nh by 2 pi. Centripetal force between the nucleus and an electron is kz e square by r square, equated to mv square by r. One r gets cancelled, the other r remains. And you know mvr is equal to nh by 2 pi. So if mvr is nh by 2 pi, r becomes nh by 2 pi mv. Simple. Substitute this formula for r, or this expression for r here. That's all. So kz e square divided by r is nh by 2 pi mv. 2 pi mv goes to the numerator, is equal to mv square. M gets cancelled, v gets cancelled, 1v remains. That's all. That's the formula for speed in the nth orbit. So speed becomes kz e square 2 pi divided by nh. So you can see that the speed of electron in the nth orbit is proportional to z by n. So ratio based questions can be asked based on this formula. You don't have to know what is the speed in the first orbit. You don't have to remember radius of first orbit of hydrogen, energy of electron in the first orbit of hydrogen. You must remember radius is 0.529 angstroms, which we wrote as 0.53 angstroms. It's called the Bohr radius. Energy of electron in the first orbit is minus 13.6 electron volts. Okay, those values you need to remember. Speed value is not necessary, but ratio, to answer ratio based questions, Just remember that it is proportional to Z by N. Okay. Next, time period of revolution of electron. If it is uniform circular motion, there will be a well-defined time period in which it completes each revolution. Now you know time period is 2 pi r divided by v, time period of circular motion. You know the formula for radius of nth orbit. You just saw the formula for speed of electron in the nth orbit. Substitute them, you will get the time period formula. But if you just want to know what it is proportional to, see, radius is n square h square by 4 pi square mk z e square. Radius is proportional to n square by z. Okay. And speed we just saw is proportional to z divided by n. Therefore, time period which is proportional to r by v will be proportional to n square by z divided by z by n. N goes to numerator, z and z get multiplied, n cube divided by z square. Okay. You should know how to derive these. Well, basic formula for time period of uniform circular motion, 2 pi r divided by v. Radius is proportional to n square by z, v is proportional to z by n. Substitute, you see that time period is proportional to n cube by z square. And inverse of time period is called frequency of revolution. You can calculate that also. So if you want, you can do exact calculation. If you only want to answer ratio based questions, then you can use this proportionality. Okay. Fine. I'll just give you some more ideas. Basically, these are slightly high level. Suppose this is an alpha particle. And let's say it is fired straight towards a nucleus. If the alpha particle is fired straight towards a nucleus, then it slows down, stops at a certain distance. Okay. And then returns back also. Okay. So you know how to calculate that stopping distance, all those things. If the alpha particle is not fired straight towards the nucleus, then basically it doesn't stop. It only deviates and goes away in some other direction. Okay. Up to some distance, it travels almost straight. Okay. Till the force from the nucleus becomes significant, it will almost travel straight. After that, it starts getting deviated. And it deviates this way, turns away like this. Okay. Or it all depends on the speed with which it is fired. It may go quite close to the nucleus before undergoing a significant turn. So there will be one position where the alpha particle is nearest to the nucleus. Okay. Now, the distance between the line of action of initial velocity of the alpha particle and the nucleus, this distance is called the impact parameter, B. And let's say you know with what speed the alpha particle has been fired. U. Mass of the alpha particle, charge of the alpha particle are also well known. And the charge of the nucleus is given to you. You know nucleus is considered to be fixed. It doesn't move when an alpha particle approaches it. Can any of you tell me an idea? Suppose all the other things are given to you. Can any of you tell me an idea to calculate this shortest distance of approach now? You know the mass of the alpha particle, let's say you know the charge of the alpha particle, and you know with what speed it is projected, means you know its energy, and you know from where it is projected also. It is projected from a very large distance, infinity. How close does it get to the nucleus? Think about it. I'll give you a minute. Think of some idea. I don't want the answer. How can you calculate this? And this same question can simply be asked in electrostatics also. See, these are just two charged particles. Okay. How close are they going to get? And this same questions can be asked in gravitation as well. And in gravitation, it holds a lot of significance. Okay. Why? Suppose there's a planet. Let's assume planet to be stationary. Okay. And let's say there's an asteroid somewhere nearby. The asteroid could be moving towards the planet, not directly towards. If asteroid is moving directly towards the planet, it will hit the planet. Okay. But suppose the line of velocity of the asteroid is initially like this. Okay. So had there been no gravity, the asteroid would have gone straight. But the planet will exert gravitational force on the asteroid as it comes closer. As a result, what will happen? The asteroid's path or the asteroid will deviate from this path. If the gravitational force of the planet is too strong or if the impact parameter is very less. Okay, this is impact parameter, no B. If the impact parameter is very less, then the gravitational force of the planet could attract the asteroid and the asteroid can hit the planet. Okay. Suppose the impact parameter is large enough or the speed of the asteroid is large enough. It's possible that the asteroid just takes a turn like this, gets close to the planet, but goes away to infinity again. Okay. So you should be able to tell how close it gets to the planet. The idea to solve this problem is same as the idea to solve this problem. Okay. So think about this, all of you. If all the other information is given to you, how will you find out that shortest distance? Any idea, anyone? Okay. To solve any such problems, you first need to understand why this is happening. Now, why is the path of the alpha particle getting deviated? Because of repulsion from the nucleus, electrostatic repulsion, which is conservative in nature. And you need to know how close the alpha particle gets. You are asked about its distance between two charges. Now, whether it's distance between two charges or distance between two masses like an asteroid and a planet, the forces involved are conservative forces. Gravitational force in this case, in case of charges, electrostatic force. So mechanical energy conservation is one idea that can be applied. And mechanical energy conservation involves distances. How do you apply mechanical energy conservation? Potential energy plus kinetic energy initially is equal to potential energy plus kinetic energy finally. The potential energy between charges or masses depends on the distance between them. So if you want to bring distance into the equation, potential energy is one quantity which can help. So energy conservation is one idea that you can use. So initial potential energy plus kinetic energy is equal to final potential energy plus kinetic energy. Now, initial potential energy, we are assuming the alpha particle is initially at a very large distance. Okay. So if the distance is very large, tending to infinity, then the initial potential energy becomes zero. So Ui is zero. Ki, I told you all the required information is given to you. You know with what speed the alpha particle is fired, or they may directly give you the energy with which it is fired. Okay. So that energy is the initial kinetic energy. Should be equal to final potential energy. Finally means where the alpha particle is closest to the nucleus. Okay. The separation is D. Then the potential energy becomes K. Q1, charge of an alpha particle is 2e. Q2, charge of the nucleus is Ze, divided by distance between them, D. K Q1 Q2 by D is the potential energy between two charges. And both are positively charged. So this is the final potential energy plus final kinetic energy of the alpha particle, half mv square. Now what we are interested in is calculating the distance D, but we don't know what is the speed there at that moment. If you can somehow find out the speed at that instant, okay, you can substitute it in the energy conservation formula and tell the distance. How to find out the speed? Again, the force which is making all this happen is the electrostatic repulsion between the nucleus and the alpha particle. In case of planet and asteroid, it's the gravitational force. The electrostatic force of repulsion between the nucleus and the alpha particle is always along the line connecting them. Okay. So initially, the electrostatic force. Initially, it is at infinite distance. You don't have to bother about the force. But just saying, initially the force is acting along this line, repulsive force. Later, when the alpha particle comes to some place here, the force, the line of action of the force will be this. Okay. Finally, when the alpha particle is nearest to the nucleus, the line of action of the force will be this, and so on. You can see that the line of action of the force always passes through the nucleus. And there is something we can do if the line of action of a force always passes through a particular point. If line of action passes through a certain point, torque produced by that force about that point becomes zero. And if torque is zero, you can apply angular momentum conservation. Angular momentum conservation also involves speeds and distances. Okay. Now the alpha particle is a particle. How do you write angular momentum of a particle? L is equal to mv r perpendicular. Mass of the particle, velocity of the particle, and the perpendicular distance from the line of action of velocity to the axis about which you are conserving angular momentum. Okay. So you can write L initial is equal to L final for the alpha particle. In case of planet and asteroid, you can conserve the angular momentum of the asteroid. Initial angular momentum is equal to final. Now let's see how to write equations based on this. Initially, the speed of the alpha particle is u, and you know the line of action of its velocity, that horizontal line. What's the perpendicular distance from the axis to the line of action of velocity initially? It is this, the impact parameter itself. That will be given to you. Without that, you can't do these calculations. Okay. If you know how it is fired only, you can tell how close it will get. So initial angular momentum of the alpha particle is simply m speed u. The perpendicular distance from line of action of velocity to the axis is the impact parameter b. Should be equal to angular momentum at any other instant. Now consider the angular momentum when the alpha particle is closest to the nucleus. When it is closest to the nucleus, its velocity will be perpendicular to the line connecting them. That is when it is closest. So at that instant, when it is closest, the perpendicular distance from the nucleus to the line of action of velocity will be d itself, the distance we are looking for. So the final angular momentum can be taken as m, the unknown speed v, multiplied with d. That's all. Now we have two equations involving v and d. So we can solve. Okay. Take v from the first equation and put it in the second equation. You will get d. Or you take d from one equation and put it in the other equation. You will get v. Simple. So remember, such questions can be solved using energy conservation as well as angular momentum conservation. Okay. There's one more idea also. For mains, this is not necessary, but you should know how to do it. I won't explain now. I'll just give you a brief idea. Suppose there's an alpha particle. The charge, mass of an alpha particle are all well defined. So we know its mass, we know its charge. And let's say you know the speed with which it is projected. And assume it is projected like this. Towards a nucleus, not straight towards a nucleus, but it is projected like this. Okay. Let's say the nucleus is somewhere here. So the initial line of action of the velocity of the alpha particle does not pass through the nucleus. So had there been no electrostatic force of repulsion, it would have gone straight like this, missing the nucleus by a certain distance. And that distance is what we call as the impact parameter. So let's say the impact parameter is known to you. And assume the alpha particle is fired with a speed u. If the speed is very high, the momentum will be very high. And if momentum is very high, it is difficult to deviate the path of an object. Higher its momentum, more difficult it is to cause a certain disturbance. Okay, that's why we say momentum is a measure of inertia of motion. What is inertia? The resistance of an object to a change in its state. Okay, or how difficult it is to change the state of motion of an object. That is what is inertia of motion. Momentum is a measure of that. So if you increase the speed of the alpha particle, speed of projection of the alpha particle, it will have stronger or higher momentum and it becomes more difficult to deviate it. So greater speeds will suffer lesser deviations. So at the same impact parameter, you fire different alpha particles, many alpha particles with different speeds, then also the deviations will be different. One of them may deviate only a little bit like this if it is going quite fast. If it is going very slow, what will happen? Deviation will be significant, significantly large, because electrostatic force will start showing more effect on it, on its path. Okay, so it depends on how much an alpha particle deviates, depends on the speed of projection. And of course, it depends on impact parameter also. With the same speed, if the alpha particle is fired directly towards the nucleus, it suffers a deviation of 180 degrees. You know, it goes straight back. Okay. But if it is not fired directly towards the nucleus, then the deviation varies. Greater the impact parameter, lesser the deviation. So the deviation suffered by an alpha particle depends on the speed of projection. Okay. Of course, mass, charge, and all are fixed. Okay. It depends on the speed of projection and it depends on the impact parameter. Based on this, you can tell what is the deviation that it suffers. Okay, finally, let's say this alpha particle goes off like this. Then if you draw tangent to its path, initial, final, you will be able to visualize a certain angle of deviation, theta. Theta depends on the speed of projection and the impact parameter. There's a formula also. For mains, even for advanced, that formula is not needed. But if possible, you just go through how it is calculated. It involves the concepts that you learn in your syllabus only. Okay, it involves the idea of average force being, okay, average force being change in momentum divided by change in time. Okay, and then some conservation laws. Okay, I'll record a video on this and send if you want. Right now, we'll not be discussing. It's a very lengthy derivation, but it can be derived using the concept that you learn in your syllabus. So you can tell by what angle an alpha particle deviates also. And same idea can be used in gravitation. You can tell by what angle an asteroid deviates when it goes close to a planet. Okay, fine. That is all there is in this chapter. Dual nature, atoms, very simple chapters, and you will definitely have questions from these. So practice problems, at least 10 problems based on each idea in these chapters. Spectral lines, 10 problems. Bohr's model of the atom, energy calculations, radius calculations, time period, speed calculations, 10 problems. Okay. And Rutherford model, shortest distance of approach between an alpha particle and the nucleus, few problems based on that. Okay. Fine. Next class, which will be on Saturday, we'll start the chapter nuclei. Nuclei is also a very small chapter. Now they have even removed radioactivity. Radioactivity will be there for JEE Advanced. For mains, it is not there. So as of now, we'll not be discussing it. Other things we'll discuss and we'll solve problems based on that. Okay, thank you all. We'll continue in the next class.